Quantum.
This is beautiful.
With mics. Yeah. Okay, so your special relativity essays from the first homework assignment are being handed back to you. And I hung on to them intentionally to give you some time to mature your understanding of special relativity as per this class. So hopefully you'll look back on these with, I don't know, as much fun as I had when I wrote them.
Uh-oh. Did you give us comments?
No, I did not give you comments. You all got
Just select them to laugh at our ignorance.
No, it was not as much for me as it was for you. Okay, so before we have a lot to cover today, so I'm going to go chop here. Before I get started, are there any questions, outstanding questions from last time? Okay, so one of the big lessons that we learned from last time is we get a lot out of demanding things be tensors. Okay, we saw that in trying to generalize the notion of three-dimensional velocity to four-dimensional velocity and wanting the resulting quantity to be a good tensor, that means it transforms like a tensor should. We had to redefine how we take the derivative, introduce this parameterization tau, and it led us to a lot of interesting results. Well, that theme, I cannot stress how crucial that theme is throughout the entirety of this course. We're going to use it again today. We're going to talk about things that we think should be tensors, and then it's going to turn out they're not, and then we have to fix them so they are, and it's also going to play a very, very big role in formulating general relativity, the physics of curved spaces when we get there. We're still in special relativity in case it's not obvious. All right, so in the course of today's discussion, which I will admit is going to be very technical, we are going to unearth perhaps what to you might have been a mystery all along, which is we have this quantity in physics called the energy momentum 4 vector. And we talked about this last time, how this thing has a time-like component, which is essentially the relativistic energy of the system. And then it has spatial components, which are the relativistic momentum of the system. And, you know, we kind of know what that thing describes. You got some particle and it's zipping along with some energy, some mass that contributes to the energy through the rest mass energy. It's got some more conventional kinetic energy terms, and then of course it's got a momentum. Okay? So that's something which you worked with in Physics 1. This is just the relativistic version of it. Nothing new there. However, many of you are familiar with the fact that at various places in physics, you also encounter this thing, which is called the energy momentum tensor. And the fact that it has two indices tells us that if we want to display its components, we would naturally do that in terms of a matrix. And so you might be scratching your head saying, well, if we've got energy and momentum captured in a 4 vector, why the hell do we need this? Why do we need an energy momentum tensor? Why can't we just work with this? And that's what we're going to unearth today, is why do we need that? What is it? And what does it look like for a couple of examples? Okay? So there's going to be, hopefully at the end, I'll kind of point to this is the thing you really need to remember and work with. A lot of the details of what goes into this is sort of, you're not really going to be held that accountable for, so just kind of sit back and enjoy the narrative. Okay, so to motivate what I'm about to say, when we are dealing with general relativity, there's always two sides to the coin. One is we have stuff we call sources which create geometry. And I'm prefacing this in the context of general relativity, even though we're still working in special relativity, because I can't really motivate it in special relativity per se. But in general relativity, we've got sources which create curved geometry, and then we're going to study like little test masses as they move through the curved geometry. Now, when we deal with a little test mass, it's going to be sufficient to talk about the 4 momentum of the test mass, because it's an object and it's moving and it's got energy and momentum. But when we talk about the sources, the stuff that's actually creating the curved geometry, in that case, you can imagine that we're probably going to be talking about large collections of objects. Okay, the many atoms that make up a planet, or all of the planets and stars in the galaxy, or in the entire universe. So in that sense, it's going to be less relevant to think of individual momentum terms, and rather, we want to think about a density, something like a momentum density. Okay, or an energy momentum density. All right. And I would argue to you that it is because you're interested in creating a density, which is relevant for large objects or large collections of things, this is eventually what is going to lead us to have to introduce this thing called the energy momentum tensor. Okay? But getting there is going to be a bit of a story. So here we go. So we're going to start with just the general notion of densities in special relativity. Because it turns out that densities in special relativity, like lots of things in special relativity, are considerably different than densities in non-relativistic physics with which you are familiar. So we're going to start with a very simple example. It's sort of the most simple example. And we're going to talk about particle number density. Okay? And I'm going to define things sort of locally, so I'll just talk about differential quantities. So we'll have a differential volume, a differential number of particles. So there's going to be lots and lots of D's in here everywhere. And that's just because ultimately we might be interested in some kind of density that's not uniform, that varies throughout space and time. And so we've got to be defining things in differential amounts, and then we can have some functional form to that. So particle number density, if we have a number of particles, which I'm going to call dn, and again, it's a small number of particles, and those particles are sitting in some small volume dV, then I can use that ratio to define what I will call the infinitesimal number density. And it's probably obvious that this quantity sitting in the numerator is a scalar, because it is literally the number of particles. You could count it on your fingers, and that doesn't matter. If I count 6 particles and then I'm traveling at, half speed of light, I'll still see 6 particles. Okay, that number doesn't really do anything interesting. The bottom, though, it's a little bit of a problem child. This is where we're going to encounter some interesting effects. And in a simple Cartesian coordinate system where we think of our volume as just a cube with its edges sitting along the coordinate axes, we can just express dV in terms of dx, dy, dz. And then we can take this general definition, and so we imagine we've got this cube, and its edges are just sitting on the coordinate axes. And I'm not going to use a right-handed coordinate system because I'll do this. Anyway, so we're going to have, a collection dn of particles sitting in this little volume. And the edges of this are all going to be length dx, dy, dz. And then we can imagine being in a reference frame where overall these particles are sitting at rest. So the volume that we're seeing is overall at rest. And so that would lead us to define a quantity called the rest number density. Which we could write like that. Again, it's the same number of particles, it's just we're going to be looking at we're going to be looking from the reference frame where the box itself is at rest, and so there's going to be a volume associated with it that is the rest volume. And now the question is this a tensor? Victim number 1. Jonathan. Is Jonathan here? Sarah Jones. If I want to know if this quantity is a tensor, what could I check?
To see how it transforms?
To see how it transforms, exactly. If it transforms like a tensor, then we're good. If it doesn't, then we're bad. Okay, so to do that, we can just imagine boosting to some reference frame. So for simplicity, let's imagine that this is the rest frame. And then what we're going to do is we're going to boost to a frame S, which is moving with a speed v along the negative x direction. And the reason I'm going to do that is because then if you're standing in the frame S, it really doesn't matter what direction we boost. We're just going to do it along the x-axis. But in the frame S, a person at rest in the frame S would then see this volume doing what?
Moving to the right.
Moving to the right, exactly. So if this person's frame is moving to the left, they will see the box moving to the right. Okay. But the good news is that we already kind of know what happens in this scenario because of what things are made of. Sorry, this should be, I'm going to call this S prime because I always prime my new frames. So in the new frame, we know that the number of particles doesn't change because that's a scalar. The volume, because I've set my box up with the lengths along the coordinate axes, the volume is composed of dx, dy, dz. Do any of those change? Say it again. X, what does it do? It contracts. Okay, dx is a length. And we know that if you boost along a length direction, that length contracts. Lengths perpendicular, or displacements perpendicular to the boost direction don't get affected. So we have length contraction on dx, and so dx is going to pick up a factor of 1 over gamma. Okay. Remember, gamma is always larger than or equal to 1, so 1 over gamma is smaller than 1, and that's making the value of the lengths along the x direction smaller. And then overall, that's going to bring out a factor of gamma in the numerator. And so our new particle number density is related to our original particle number density just by a factor of gamma. Okay. And of course, we could start with the rest density, in which case our new density would just be gamma times the rest density. If we started with our original frame being the rest frame of the object, although we don't have to do that for sure. Okay. So, Kyle, I have just demonstrated to you how dn transforms. Does this transform like a tensor? No. So I know we're still kind of, what exactly are you doing? So remember, transformation rules go like this. If I have a scalar, phi is always a scalar, but I'll just write s. If I have a scalar and I do a transformation, then the scalar, and I'm referring to the components now. We don't do any of this crap with basis vectors. If I have a scalar and I transform coordinates, the expression looks exactly the same. Okay. If I have a vector and I transform coordinates, then the transformation better look like this. And similarly for dual vectors. Okay. And then you can generalize these rules to arbitrary tensors, because they just have multiple vector and dual vector indices. So that thing only has one component, right? It doesn't have an index. So your best guess is that it might be a scalar, but does it behave like a scalar? No, it got a gamma. Okay. So this is not transforming like a tensor. All right? Now, we are going to have to fix this because we want this thing to be a tensor. So we can make an inspired guess. What does this transform like? Yeah. No.
I regret my decision to raise mine.
Okay. All right, it's fine. Does this transform like anything we've seen before?
Would it be like a coordinate?
Which coordinate?
A differential coordinate?
Of which coordinate?
I I don't know.
No, it's fine, it's fine. So I think we've seen a formula like this. Yes? But of course, this is not a tensor. This is what? This is a component of a 4 vector. So maybe we should be thinking of this dn as a component of a 4 vector, in much the way that we think of dt as a component of a 4 vector. Of course, that leads us to what are the other components of the 4 vector. So without any further ado, I will just show you the 4 vector in question. It is going to be called d capital N mu. Mu is there because it's going to be a vector, d because it's still differential, and capital N because, I don't know, it's confusing. And we are going to define this thing to be the rest value of dn, okay, where we're considering this quantity to be a constant. So when we do transformations, that is just a constant value that doesn't change. Okay, we're not thinking of this as a component of anything. We're just keeping it as a constant. It's kind of like rest mass. And then we're going to multiply that by the 4 velocity. Where the 4 velocity in question is the overall 4 velocity of the volume. Okay. So we're going to have a little arrow that tells us how that u mu is actually defined. Okay? Not to be too confusing. Okay. Now, this might seem unmotivated, but let's just see if it kind of at least gives us the right component where we expect at least one of the components to be known. If I write down the components of this thing, then we are probably going to need to remember Mr. Cold Boob. You warmed up yet?
Yeah, I'm rubbing it and now I'm warm.
Okay. For anyone that came in late, you missed it. Avery, what is the time component of the 4 velocity?
Gamma.
It's just gamma, and what about the spatial components?
Gamma and then the velocity of the particle.
Yeah.
Velocity.
It's the spatial components of the velocity. Okay. So we could also write it like this. Okay. Oh, that's interesting. Didn't you say earlier that if we started from the rest frame and we transformed to another frame, that our number density, naively defined, should transform exactly like that? Okay. Alternatively, if we take this definition and we evaluate this vector in the rest frame of this volume, what is gamma? So remember, gamma is 1 over the square root of 1 minus v squared, where v is the velocity between the two frames. So if you're in the rest frame, then your relative velocity to the rest frame is 0, so gamma is 1. Here's the harder question. If you're in the rest frame, your relative velocity to the rest frame is 0, so what's the relative velocity between you and the rest frame? 0. I know, get you guys thinking. 0. Okay, so we've got some evidence that this definition is making sense. The good news is that the way it's defined as a constant, that it doesn't transform, this is just a constant, times a legitimate vector. We spent last time talking about how the 4 velocity is a real vector, okay? This quantity is guaranteed to be a vector, okay? So to summarize the lesson from this, because it's going to get more complicated when we step the discussion up, we started with a scalar dn. That is, we started with the number of particles that was sitting in some region. But to make a density, we had to introduce a vector. Okay, it wasn't sufficient to take the scalar and divide it by a volume and say that the density itself would be a scalar. No, the density required us to look at a sort of higher rank tensor. Okay? Now, this might have seemed like a guess. You might wonder if there are other options. But I'm actually going to go through a little bit of a sort of a deeper explanation of why we should actually expect this to be the case. Why is it that if we start off with a quantity and then we want to create a density associated with that quantity, we should generically expect the tensor nature to get higher? So here we went from scalar to vector. That's actually going to be a general trend. Okay. So why in the world would this have to be? In 3 dimensions, to specify an area, you need a size and direction. Okay, you're all familiar with this from as early as I think physics 2, where you would create little areas. A lot of times these are Gaussian surfaces, and then you would identify the direction of the surface by a normal vector, dA, which is perpendicular to the surface in question. Okay? And then you could integrate it over this to get the area of this thing, et cetera, et cetera. But the point is that when you consider an area in 3 dimensions, it's not enough just to give the size, because I could take a disk in 3 dimensions and I could orient it any way that I want. And so for a unique specification of an area, I have to not just give you the size of the thing, but I have to tell you what orientation it's in. And in 3 dimensions, that orientation can be specified by a normal vector. Okay? Now, I would argue to you that in 3 dimensions, this thing is actually not a vector, but a dual vector. Okay? And I'll argue it to you in the following way. So one way to identify a 2-dimensional surface, which is obviously relevant for an area, if you're in 3 dimensions, so a 2D surface in 3D can always be specified with some function of x, y, and z that's equal to 0. Okay? And then from this function, you can create the normal vector. Let me show you how. So as an example, let's consider the 2-sphere with a radius r. And we know that a 2-sphere radius r, which is centered around the origin, is described by... I'm having the hardest time writing z today, and equal signs. Okay, it's specified by that equation. We've all seen that before, right? Okay, here we go. Who is my next victim? Hey, Julia! Yo, Andrea. Here's an equation. Take this equation and make it like that. What would you say? Take this equation and make it like that.
X squared plus y squared plus z squared minus r squared is equal to 0.
Oh, you're so smart. Okay? Okay, good. Yeah, so there's your function. Once you have the function in hand, to find the vector that you might call the area vector, all you do is you take partial derivatives of your function with respect to your coordinates and multiply them by the appropriate basis vectors. And of course, for this case, this would just be 2x I hat plus 2y j hat plus 2z k hat, which if you were smarter, you would just convert it to spherical polar coordinates, where this would just come out to be 2r hat, which you know is perpendicular to the surface of the sphere. The radial directions are perpendicular to the surface of the sphere, so at the origin. Okay? But notice that this construction uses d by dxi, which is of course di, that's got that dual vector nature. It's like a derivative with respect to coordinates, and that's how we know that this area vector should be thought of as a dual vector and not a vector. Okay. It's going to be important in what's coming next. All right, you ready? In 4D, if you want to specify a 3D volume, you need both a size and a direction. It's very hard to picture, as are most things in 4 dimensions. That's why we started with the concrete case that you can picture. But the issue is just that you've got a volume sitting in a space which is one-dimensional higher. And that means that there's a direction associated with that volume. And because it's in exactly one dimension higher than the volume in question, we can describe that direction by a dual vector. Okay? So without any further ado, a volume in 4-dimensional space-time, where what I mean by volume is a 3 volume in 4D is specified by, and I'm going to put this away because that's not even a piece of paper I should be looking at. This one. Here it is. Should be specified by, I can't tell my etas from my ends, a dual vector, which I might as well just take it to be the unit dual vector. The unit dual vector times the size of the volume in question. Okay, and if I'm thinking about a differential volume, I'll just make it a differential size. Okay. So this is what's playing the role of dA that you're used to working with in electromagnetism. Okay. Here we're just being a little more precise because we know it should be a dual vector, so when we put in the directionality, we put it in as a dual vector. And then we're going to capture the size in dV, so this is just going to be the unit dual vector. Okay? Where this thing is orthogonal to the 3 volume in 4-dimensional space. And everything I'm saying can be in space or space-time. Like you could do, all this pertains to 4-dimensional space or 4-dimensional space-time. This is robust. Okay. So now let's actually look at the more sophisticated version of something that you've played with many, many times. And that is the following. If I gave you a density dN over dV, so a number of particles per unit volume, and then I gave you a particular volume, and I said, how many particles are in that volume, what would you do?
Multiply the density by the volume.
Give that man a cookie.
Do you have cookies? Did you bring cookies?
I didn't bring the cookies. I forgot the cookies. Yeah, exactly. You're totally right. That's what you do. So I just multiply this thing by the volume, and I get this sort of trivial math statement. dN equals dN over dV times dV. Okay? But now what we realize is that this story is not really well suited to four-dimensional space-time. And the way our story plays out is as follows. If I have the density, which now remember is a 4-vector, and I want to know the number of particles, which should be a scalar, in a given volume of space-time, I multiply it by the volume of the region of space-time, which is, of course, expressed in terms of a dual vector and a volume size. And that gives me the scalar number of particles in that volume. Okay? So you now see that it's sort of by virtue of this fact that when we talk about creating densities, we're talking about something per 3 volume. But because 3 volume requires this normal vector, which normal dual vector, to create a real scalar at the end of the day, where if we're starting with a scalar, we want this to be a scalar, number of particles, we've got to be combining the dual vector that defines the volume with a vector, because clearly a vector and a dual vector combine to give you a scalar. Okay. You had no hope of working with this being a scalar, because if this had ever been a scalar, then this being a dual vector would have created a dual vector density. Okay. I really need you on board with that for what I'm about to say. Is everybody on board with it? Is anybody bothered by it? You're bothered by it?
A little bit.
Okay.
It seems weird that in this, you need the kind of direction or orientation of this three-dimensional piece for your, and multiply that by your density, and then it changes your total number of scalars. It's just a little counterintuitive. So why do you need the n component here for that calculation?
Why do I need the
dual vector.
Why do I need the directionality? I would say it's probably akin to, let's suppose that in 3 spatial dimensions, this is of course the context where you've seen this, you've got some electric flux lines. And then I ask you, what is the flux density per unit area? That in and of itself is not well defined, because I have to tell you how the area is oriented. Because I could take a fixed area size, but then depending on how it's oriented, I'm going to get totally different answers for the density of field lines. Okay. Other. Okay, well, here we go. Here we go. Buckle up. All right, what we're really interested in doing now, we're going to leave behind this simple example. What we're really interested in doing is thinking about P mu, that is energy and momentum, but we want to create a density out of it. Yeah. Why? That was what I said earlier, because sources for general relativity usually involve large collections of things.
Okay.
And so we want to think about densities.
So it's about ease of calculation?
Yes.
Okay.
So, well, no, it's not about ease of calculation. It's the fact that you're distributing energy. So normally you're used to thinking of there's a particle, it's got energy and momentum, and it's zipping along. But we want to think about distributions of energy and momentum. Okay, so we really need to think about densities.
Awesome.
Okay, well, here we go. I'm going to think about this in terms of a small region, so I only expect a small amount of energy and momentum there. But what I'm going to do is I'm going to calculate this thing by using some analog of energy, momentum, density times a volume. I mean, this is just, it's a volume. It's the same thing that goes there. What do I need here?
A rank 2 tensor.
You need a rank 2 tensor. Or you need a 2-0 tensor. You need something that has 2 upper indices. One to contract with the dual vector index here, and one to be left over to provide the index on the 4 momentum velocity, or 4 momentum vector, sorry. So as promised, it's in the need to create densities for energy and momentum that we go from P, mu, which we naturally think of for a particle, to T mu nu. T mu nu is the natural description of a distribution of energy and momentum. Okay? All right. Of course, T mu nu is going to play a very large role in general relativity because it is going to provide the source that creates curvature in the gravitational interaction. So this is something we really want to try and get as comfortable with as possible. So we're going to spend some time now trying to pick apart what this T mu nu looks like. And I know that some of what I'm about to say you've seen in other, or many of you have seen in other contexts. So some of this might be a review. And even if the results are familiar, the method I could use to get to them might not be so familiar. So what does T mu nu look like? And again, I want to stress to you that the theme of what I'm doing today is just like the theme of what I did last time. It's like, I want to think about this quantity, but I want to make sure that I'm working with a tensor version of it. I want to make sure it transforms properly. And it's in making sure that it's a tensor that I'm kind of led to this idea that density, an energy momentum density has to be described by a rank 2 tensor instead of just what you might have thought would be a vector. So to organize ourselves, we will write a list of matrix components. And God, I actually wrote them all down. That's so silly of me. Okay. And I'm at various points going to be looking at maybe these terms or this term or this term, so I just want to get that up there so you know what I'm looking at when I look at particular terms. Now the good news is that T mu nu is symmetric. So to give an interpretation to the elements of T mu nu, I really only have to take, one half of this, or one triangle of this, because you have to do the diagonals, and then I just pull these things out. Okay, so there's 10 terms that we need to give interpretations to. And then with those 10 terms in hand, you can figure out the other 6 off diagonals. Okay, so here we go. To give these things interpretations, we're going to basically consider different types of 3-dimensional volumes in 4-dimensional space-time. And that's non-trivial. Okay? So consider first a normal vector, a normal dual vector, which is of the form 1, 0, 0, 0. So remember, that's the 0 component. This is clearly normalized to 1, or minus 1, actually. But what type of volume in space-time is this normal vector describing? So the normal vector points in the time direction. The volume is perpendicular to the direction the normal vector points. That's how we define this thing. So what kind of volume are we talking about in this case?
Regular 3D volume.
Yeah, it's a regular 3D spatial volume. So in this case, we could call our dv element, if we so choose, dx, dy, dz. Okay? Now let us remember the components of the form momentum are the relativistic energy and the relativistic momentum. The relativistic just tells us it includes the non-relativistic pieces like 1/2 mv squared and mv, but it also includes the rest mass term and then all these higher order corrections. Okay, so here we go. Now our defining equation here we can think of as this expression dp mu is t mu nu n nu dv. That's what we just kind of finished with in our previous discussion. And we can use this to define for us the components of t mu nu. Because we know what the components of this is. If we're just looking at a small amount of energy momentum, then those are just d's everywhere. So we know what this is. I can look at various cases for what this quantity is. Here's an example. And then I can just plug all that in to figure out what t mu nu is. Okay? So let's do it. The nu is going to get summed over. But when I sum over it, the only contribution is going to come from nu equals to what? Dylan, honors.
Zero.
Dylan? Zero. Oh, there you are. 0, right. It's only going the only contribution to nu is going to come when nu is equal to 0 because that's going to be 1. And so we might as well put a 0 there. I could put in 0 there, but that's just 1. So we have that. Okay? Now, this expression has how many components? This expression gives rise to how many different expressions, Chase? 4? 4, right. It's got a mu index, and so I can take 4 different values for mu. All right? We only really need to consider 2. We can think about when mu is equal to 0, and then we can think about when mu is a spatial index, because it doesn't matter which spatial index you pick, it'll probably be the same. So if we pick mu to be a 0, then I have T00 dV, which tells me that T00 is dP0. What is dP0? Yeah, it's the dE over dV. It's the small amount of energy in a small volume. We call that the energy density. Where here density refers to the usual dividing the energy by the spatial volume in which it's encapsulated. Alternatively, if I pick mu in this expression to be a spatial index, then I have something like that. And this might not be as obvious, but this means that the Ti0 component is the momentum density in that same, and we do have a name for it. We'll call it pi I. So this is the amount of spatial momentum, relativistic spatial momentum contained in that volume. Okay. And then we'll remember that by the symmetry of the energy momentum tensor, we can always also interpret that as T0I. Okay? So if we look up here, we've basically got that T00 in this bad boy is just the energy density, and this string of components is essentially the momentum density, and so too are these components. Okay? So now we've got this 3 by 3 block down here to give an interpretation to, and how do you think we're going to manage to give that an interpretation? We still have this defining equation, so if we want to get some new information, what are we going to have to do? Yeah, pick a different normal vector. Okay? So now let's consider n mu equals to, and it really doesn't matter which one we pick, that's sort of the theme of this. Once you go from time to space, it doesn't matter which space you pick. But let's pick our normal vector to now point along the x direction. And in this case, dv is now equal to what combination of differentials, Ryan? Yeah, it's dt, dy, dz, which I'll just call this the area in the yz plane. So now we're looking at something weird. We're looking at a three-dimensional volume in space-time where that volume includes time as one of its elements. But that's fine. I mean, we can do that. There's nothing that says we can't consider a three-dimensional volume in four-dimensional space-time which combines space and time. And now we play exactly the same game. This time, the only index on this summation which is going to contribute is nu equals to 1. Okay. Where we'll substitute in our dv expression. And then once again, we have 4 different contributions to this for different choices of mu. And we can start with the 0th contribution. Oh, we've already done that one. We don't actually need to worry about that because we've got it here. And doing the momentum flow is a little bit more tricky if you start with this normal vector. That's why we actually did it this way. But at the end of the day, you will get the same expression. It just involves some extra steps. So what we're going to do, though, to get something new is to think of the mu as a spatial index. And actually, yeah, okay, so let's first pick a spatial index which is the same as this guy. And then secondly, we'll pick a different one, say 2. Okay. Now if I take this guy and I solve it for t11, I've got dp1 over dayz dt over dayz. No, hold on, confusing myself. Oh yeah, it is over 1 over dA, ayz. Okay. And then of course here we'll have t21 is dp2 dt over dayz. dp1 dt, what do you think that is? dp1 dt. Let's be brave. Let's call that the derivative of the ith component of the momentum with respect to time.
Force.
It's force. It's the x component of the force divided by the area of the yz plane. Okay? So let's do this. Let's have a plane that's spanning y and z. We've got some force, which is actually distributed over this. And what we've just found is the x component of that force divided by the area of the plane. What do we call that? It's pressure. Here, dp2 dt is F2 over day dz. Now we're looking for a component of the force which is parallel to the plane. What do we call that?
Shear.
Shear. So what we've discovered is the interpretation of the components of the energy momentum tensor is that the spatial components along the diagonal are giving us the pressure, and then our spatial off-diagonal elements are telling us about the shear. So so just so you're aware, all of this line of argument, you're probably going to do a chord number. It's okay. If you walk out of here knowing anything, it's first of all, why does energy, momentum, density need to be described by a tensor? Why couldn't we just have gotten away with a vector? This picture right here is something that should stick. Most notably, these diagonal terms. Most of what we'll deal with in this class will only be working with energy momentum tensors with non-zero diagonal terms. Okay, occasionally we might have a momentum density, right? All right, so we've got some kind of interpretation of what the components of this thing are. Now let's look at some very, very concrete examples. The kinds of energy momentum tensors that we're actually going to encounter when we do calculations. So I've got these words up there, I've got some formulas we used, but let's actually see what things are going to look like for reals. So before we get into concrete examples, there is a little trick that we need to consider, which is going to make interpreting things very nice. Our expression through one of those algebraic processes on very fancy tensorial objects that you just totally feel like you can't do, would lead us to say that T mu nu is P mu over N nu dV. Okay? We kind of did that in what we were talking about earlier with the various components, but you know, like, is this legit? Can you divide a vector by a dual vector? Does that division even make sense? I don't know. Did you learn about division of vectors when you were studying vectors in calculus or physics 1? I don't know, but just bear with me. Let's see if we can make sense of this. So remember that our number density vector, d and mu, we could define to be the rest density times the 4 velocity. That's the 4 velocity that connects your reference frame to the overall rest frame of the volume that contains the particles in question. But dn rest is simply the total number of particles in question divided by the volume of the region in the rest frame. So this is just dn rest is the number of particles divided by the volume in the rest frame. However, we also know that dn mu, according to a prescription like this, would be written as dn divided by the volume in question. This would be a lower meter. So I'm just trying to take the analogous statement to this for the case of the number density vector. equating these, so equating this expression to this expression, what we find is that taking out the dn, we have 1 over n mu dv is equivalent to u mu over dv rest. Okay. Now, if I apply this to this wonky-looking expression for the energy momentum tensor, then we can say, I'm just going to replace 1 over n mu d nu with this guy, and so this is going to become, this should be differential amounts of momentum. This is going to become the differential amount of momentum contained in said volume times the form momentum connecting the frame I'm sitting in to the rest frame, overall rest frame of the collection of objects, divided by the rest volume. Okay. So this is actually going to give us a slightly easier thing to work with, because we can sort of define our system or our volume in the rest frame, the overall rest frame, and that's going to be some size here. And then we can talk about, if we're moving with respect to it, what is the overall force velocity describing our relative motion with respect to that frame? Go ahead.
Should the u mu be u nu instead?
Oh, sorry, yeah. Sorry about that. Okay, there's nothing insightful about this. This is just a technical rewriting, but when we apply this to examples, this rewriting is going to make things a little bit more concrete. So let's look at some examples. So we'll start with something we call dust. Okay. Our technical definition of dust is a collection of particles at rest with respect to each other. Okay, so if we are considering some region dV, then dust, and I'm going to consider this to be the rest, then dust is just a bunch of stuff in that volume, and everything is sitting perfectly still. Okay, the volume is sitting still, the particles are sitting still in the volume. And what we would like to do is figure out what is the energy momentum tensor associated with this. And, or in particular, what is the energy momentum tensor in an arbitrary frame? And so what we do is we give our collection of dust some overall force velocity by simply shifting frames. And if we consider the volume moving to the right, then the particles in question are going to have a momentum pointing in which direction? To the left. Okay. So we're going to have an amount of momentum, again it's still a small amount because everything we're considering is small, we're going to have an amount of momentum which is basically the number of particles in the region times the mass of each particle times the force momentum. Or times the force velocity. Okay. This is basically p mu for each particle. And so we just multiply by the number of particles. That's the total amount of energy momentum contained in this region. Okay? Where bear in mind that this one force velocity is the same for all the particles in question, because they're all at rest with respect to each other. So if we boost to give one of them a force momentum or force velocity, they all get the same force velocity. All right, so here we go. Using this definition of T mu nu, we have T mu nu is dP mu. So that's the amount of form momentum as seen in this frame. So we're going to have dn m u mu times u nu divided by dv rest. Okay. dn over dv rest is just dn rest times the mass of the particles times the product of these two four velocity factors. Oh, wait a minute. This is basically the particle density. It's the number of particles in the rest volume as seen in the rest frame. And then this is the mass of each particle. Well, if I'm at rest, if a particle is at rest, what does m represent? It is the rest mass, but if you're at rest, what does it represent? It's the rest mass energy because it's secretly mc squared. But if you're at rest, what does that represent?
The energy momentum for vector the first component.
Well, it's all the energy you have.
Yeah.
Like if you're at rest, your rest mass energy is all the energy you have. Like if you're moving, you have your rest mass energy plus some counter, something that is associated with the fact that you're actually moving. But if you're at rest, your rest mass energy is all you have. So we might as well just call this the rest energy density. All right? So my argument is that for dust, this is a good definition of the energy momentum tensor, but let's actually see this in a little bit more detail. In the rest frame itself, because this definition works for any reference frame, that's the whole point of this. I want an expression for the energy momentum tensor that's true in any reference frame. If I am actually going to be in the rest frame of the dust itself, what four velocity vector should I be using?
0 to 0.
Yeah, 1, 0, 0, 0. Remember, four velocities are gamma v, where the v that appears, or sorry, v, gamma, gamma v. Where the v here and the v that sits inside of the gamma factor are the relative velocity of the two frames. So if you're in the rest frame, then the four velocity is just 1, 0, 0, 0, 0. This is a two-index object, okay? So if I want to identify the components of t mu nu, I just think about the components of this. So in particular, the t00 component is the 0 component of this, which is 1. The 0 component of this, which is 1, times rho. What are all of the other components of the energy momentum tensor in this frame? They're 0. Okay? Because if you take either mu or nu to be non-zero, then it's 0. But if you think about it, that makes sense. Because according to this interpretation, if we've got a set of particles that are sitting at rest with respect to each other, at rest with respect to the volume that we're considering, there should be no pressure. Pressure comes from particles banging into the walls. Shear comes from particles skimming off walls. Nothing is moving. All of these terms should be 0. And the momentum, what did I call this? The momentum density, sorry, the spatial momentum density should also be 0 because nothing is actually moving. The only thing that exists is the energy, and it's the rest energy associated with these things. So from our specification of dust, we could have actually guessed that in the rest frame, this term would be the only non-zero thing. And everything else would be 0, which is exactly what we're getting from that definition. Okay? Now, we're going to consider one more example, and in consideration of this next example, we're going to get to a formula which is going to be very useful. So let us now consider what is perhaps the second most commonly used source, and that is a perfect fluid, or relativistic perfect fluid. So a perfect fluid is a collection of particles with random velocities. Okay, so they don't have to be sitting dead still. So this time what we can do is we can consider a rest volume to start with, but this time our particles are going to have random spatial velocities such that there's no overall spatial velocity associated with that. Okay. For perfect fluids, we typically ignore viscosity, where viscosity in the language of the energy momentum tensor is the shear. And for simplicity, we assume isotropy. That is, we assume that the x and the y and the z directions it looks the same in each one. So this term tells me that Tij is 0 for I not equal to j. Remember, I and j means you only look at spatial components. And isotropy tells me that Tii, or T11 equals T22 equals T33. Okay. So, with that in mind, if I were going to guess the form of the energy momentum tensor in the rest frame, I would expect an energy density, because there's stuff there. So I would expect a rho. Would I expect a momentum density? So the momentum density is associated with the fact, so pressure, so I've got this box, and stuff is like moving around inside of it. Pressure is associated with the random collisions of these things with sort of the edges of the box, if you think of this as actually a physical box. Shear is associated with the random collisions, the tangential components to the surface. A momentum density would be an overall momentum flux through the box. Yeah.
That Tij only counts for non-zero, like an index of non-zero, yes.
Sorry, say it again?
The Tij only counts for indices without zero, and then yes.
Yeah, sorry. When I say so mu nu is all the indices, 0, 1, 2, 3. Ij is only 1, 2, 3. Sorry about that.
Okay, so never mind.
Okay, so since I'm in the rest frame, I expect the momentum density to be 0 because there's no net momentum flowing through the box. So these are going to be zeros. Do I expect there to be pressure? Yes. And I expect the pressure contribution to be the same in the x, y, and z directions. We're ignoring viscosity. And so in the rest frame, the energy momentum tensor for a perfect fluid should just be the energy density and then the same pressure term down the spatial parts of the diagonal. Yep.
Are we ignoring shear because we're like assuming that like it cancels out because we have random velocities? Is that why we can ignore shear?
I wouldn't say that. I wouldn't say why can or when can we ignore shear. I would take ignoring shear as the definition of the system that I'm considering.
Oh, okay. So that,
It's
that
literally
is
part of the definition.
of
Yeah.
perfect fluid. Okay.
Okay, so we have two energy momentum tensors in rest frames which, kind of makes sense. The only difference is that this one doesn't have pressure, but you expect that because in the dust case, everything is sitting dead still in the rest frame. Okay? And now here comes the miracle. Are you ready?
Yes.
Buckle up. Here is the miracle. I am going to very cleverly rewrite this thing right here. I'm going to write this as rho plus p u mu u nu plus p eta mu nu. So that's energy density, pressure, pressure. Let's convince ourselves that that is at least correct. Okay? If we're in the rest frame, what are the components of u mu? 1, 0, 0, 0. So the first term, this piece right here, is just going to be rho plus p.
I'm not advanced.
And then everything else is 0. And then this term is p times the metric. Voila. P's cancel in the 0, 0 term, leaving me rho, and then I get p's down the diagonal. Isn't that amazing? It's pretty badass, isn't it?
Why is it useful?
Why is it useful? Why is it useful? Sorry, I need to write one thing here. That's the U in the rest frame, obviously, if I'm calculating the rest. It's useful because that expression, which I constructed for you in the rest frame, it's a tensor expression. It's built out of honest-to-God tensors. T mu nu is a tensor, U mu and U nu are vectors, so their product is going to give us a second-rank tensor, and the metric is obviously a tensor. If I write a tensor equation, the tensor equation is true in any reference frame. That's the glory of working with tensors. Okay? So what we find is this theme, and this is a theme that we'll carry forward in the course, and that is, there's many cases where we can go to a particularly simple setting and get an equation. Here we looked at the rest frame, where the equation was sort of simple and intuitive. If you go to a simple setting and you write down the equation, but you're very careful to make sure that your equation is expressed in terms of tensors, then you're allowed to step back and say, it is therefore true in any reference frame, no matter how complicated.
Didn't we make kind of a lot of assumptions when we were driving that? Like if there's no
This is true for a perfect fluid
Okay.
in an arbitrary frame.
But just for purposes.
Yes. Okay. Now, there are lots of examples of perfect fluids. So for example, one example of a perfect fluid is defined by T mu nu with the pressure equals to 0. And if I set the pressure equals to 0, what does this expression become? It becomes rho u mu u nu, which is exactly what we found over here for dust. Okay? So the way that we work with this, and you're going to see this in your homework, and I might have... Yeah, you'll see another example of it in your homework. But so the way that we think about this perfect fluid energy momentum tensor expression is, this is always true as long as you're dealing with a perfect fluid. And in general relativity, we can consider all of our sources to be perfect fluids, for all intents and purposes. The only thing you have left to specify is how rho and p are related. That's it. Like, otherwise, this thing tells you what the energy momentum tensor should look like. So I might tell you rho is a number and p is 0. I might tell you that rho and p are equal. I might tell you that rho and p are equal and opposite. Okay? And we'll find some very interesting examples. So you're going to have a question in your homework where you consider the energy momentum tensor for a perfect fluid that corresponds to vacuum. You might think to yourself, vacuum, that should just be 0, right? No. Vacuum has a perfectly well-defined relationship between rho and p, which is not trivial. It gives you a non-trivial energy momentum tensor, but there's a very, very good reason why that's the vacuum energy momentum tensor, which you'll explore in your homework. Okay? So when I said that I was going to point to something that you really need to get yourself comfortable with at the end of this lecture, it's this expression right here. This is what you're going to work with. This is what we're going to work with when we're doing Einstein's equations using energy and momentum as sources of curvature. We're going to work with this expression for perfect fluid energy momentum tensor. It's true in any frame because we constructed it as a tensor equation. Jason.
How can we use that for general relativity when it's constructed with the special relativity metric?
Ooh. Ooh. So what we're going to do is when the time comes and we move to curved space, we will learn a very, very nice prescription for taking things expressed in special relativity to expressing them in a general curved space.
Okay.
That's why we're spending so much time and energy getting a very sophisticated version of special relativity under our belt. Because if you get the right version under your belt, then when you move to general relativity, the tweak is relatively minor. If you're still sitting around thinking about barns and poles and twin paradoxes, you're never going to get to general relativity in a simple, straightforward way. Okay. All right. So we'll end there for today, and I'll see you guys on Tuesday.
Go. Wow, that was kind of on time today.
Any questions today?
Yeah.
So when you,
It
it was actually pretty clear.
It was just like,
I was just gonna ask, so when you have a, like a supermassive black hole